Hey Team Pika, and welcome to today's lecture. So today we're going to be solving the Schrodinger equation for not one, but two different systems. One of those systems is going to be called the particle on a ring problem, where we're going to take a particle of mass n, shown in my purple dot on the slide, and say that it has to be on some sort of ring with radius r, and it's constrained to move about in 2 dimensions, but along that ring. The second problem we're going to treat is the three-dimensional analog of this problem, where we're going to solve the particle on a sphere. The particle, again, is allowed to move on the outside of a surface of a sphere with radius r. And so those are going to be our two problems for today. And I'll give you a heads up that today's lecture is going to be some of the most involved math of the entire course. So we're kind of at a mathematical peak. And so I should give you maybe a reason or two before we get started for why we're going to tackle these problems. And there's two reasons for that. One, the particle on a ring is a really good model for rotational motion. In the last third of the semester, we're going to talk about rotational spectroscopy. And to do that, we're going to have to resolve for the rotational motion problem as it's related to the rotational motion of different small molecules that we might be interested in. So if we solve for the particle in a ring now, it's really going to help us give some insight into what that'll look like in the last third of the course. And then the second reason, and probably the more honest reason, is that where we're really trying to lead at this point in the semester is to talk about the hydrogen atom. And the hydrogen atom is the most mathematically intense thing that we're going to do this semester. And so I need some convenient way to split up the math over 2 lectures. So today, we're going to tackle the particle on a sphere problem, which helps give us all of the math for the angular part of the hydrogen atom problem. And so doing that today will get us even most of the way there for the hydrogen atom, although you don't know it yet. So we're going to take on this problem of the particle on a sphere today, and then on next lecture, you'll be introduced to the final steps for the math to do the full hydrogen atom. And plus, as a bonus, 2 of the quantum numbers that you learned about in general chemistry for the hydrogen atom, L and M sub L in this case, are going to appear and feature pretty strongly in today's lecture. So before we get going, there's 2 different reading sections that might be helpful if you're trying to learn more or try and give yourself a refresher or a slightly different perspective on today's topic. One of those is Griffiths, which I'll post on Moodle since it's not a textbook that we bought for this course. This is the reference that I like because for me, seeing the math step by step laid out in detail often aids my understanding. That's just how my brain works. A different style of reading is going to be found in Atkins, which is a little bit more hand-wavy, but one, it does a really good job of reviewing classical rotational motion. 2, it does a good job of giving you an intuitive understanding of why we would expect to see quantum behavior in this system. And 3, it does go through some of the math that's the same as what we're going to go through today. So I recommend both of those readings if you want more info. And with that, let's start talking about the particle on a ring. So to set up this problem, just like we did for particle on a box, we'll define the potential, we'll see what the Schrodinger equation is that we need to solve, and then we'll actually go through the process of solving it, thereby giving us a wave function and a corresponding set of energies. So how I'm going to mathematically define the potential is to say that so long as our particle stays on this ring of radius r, it is allowed to move freely. The potential is 0. Otherwise, as soon as it tries to leave this ring that I've given in blue, we're going to make the potential infinity to prevent the particle from escaping that ring. And this problem actually has one fairly nice chemistry example that is not a perfect model for this chemistry example, but is okay and decent. And that would be a free electron moving around in a benzene ring. So if you remember from your organic chemistry class, the benzene ring is delocalized, so that electron can move pretty freely around the benzene ring, but it's not allowed to escape the molecule or move off of the center either above or below the benzene ring. So the electron is confined more or less to 2 dimensions, so it's kind of in a plane, and also it has a radius that it's allowed to travel in, but it's not allowed to escape that radius. Now, up until this point, we've been mostly working in Cartesian coordinates, so x and y and when we start talking about three dimensions, x, y, and z. But the natural coordinate system for this type of problem is polar coordinates, where we replace x and y with the variables r and phi. And so the potential is the same, although now it kind of makes a little bit more sense where this small r is coming from. It's one of our two polar coordinates. And it's good for me to mention at this point, especially if you go looking for external resources, that way back in the day, mathematics folks and physics folks could never agree on in two dimensions what should be the names of my two polar coordinates. Should it be r and theta, or should it be r and phi? And in this course, we're going to follow the physicist notation, which means that our polar angle is going to be phi. So that's that circle with a slash through the top. That's lowercase Greek letter phi. That's what we're going to use. And as a refresher on polar coordinates, remember that the range that phi can take on is it can go anywhere from 0 all the way up to 2 pi. So let's, before we dive into the math, do a concept check. Based on the potential that I've defined here, go ahead and pause the video and see if you can answer this question. What is the probability that the particle will be found at a distance r from the origin where r is not equal to the radius that I've shown up here in this potential? So go ahead and pause the video and see if you can answer this concept check question. Okay, hopefully you were able to connect this to our particle in a box model and say that an infinite potential is another way of saying that the particle is never going to be in this location. And so in terms of probabilities, the probability that the particle will be found at a radius that's not the radius defined in the problem, that's not the radius of the ring, is just going to be equal to 0. All right, on to the math. The two-dimensional time-independent Schrodinger equation is something that we discussed in a previous lecture, and so the formula for that is the negative h bar squared divided by 2m, m being the mass of our particle. And then we have to add together our two partial derivatives, one for the x-coordinate, one for the y-coordinate, multiply that by psi, add the potential times psi, and supposedly that will all be equal to the energy of the system times psi. Just like for the particle in a box, what psi looks like for r is not equal to capital R is just 0. And so it's pretty boring. So we can focus our attention on solving for what does psi look like for a constant value of r, where psi is at capital R. And in that case, the potential is 0. So one of these terms in my time-independent Schrodinger equation is going to disappear, which is nice for us. What's not nice is that I just argued that we should be using polar coordinates to solve this problem because that's where this natural angle, or this natural variable r, will show up to describe the radius of our circle. But this time-independent Schrodinger equation is given in Cartesian coordinates, and we need to transfer it to polar coordinates. So the technique to do this is standard mathematical toolkit, but for most of us, not something we've seen before. So in this lecture, I'm going to present, without derivation or evidence, what the corresponding polar coordinate version is of this second partial derivative with respect to x plus second partial derivative with respect to y. If you're interested in seeing the proof, again, because you might be the sort of person who seeing more math can actually aid your conceptual understanding and make you feel confident with how we get from line to line in this derivation, then I've posted that proof on Moodle under our optional readings. And so without proof, apparently the second partial derivative with respect to x plus the second partial derivative with respect to y is equal to the second partial derivative with respect to r plus 1 over r times the first partial derivative with respect to r plus 1 over r squared times the second derivative, this time with respect to phi. And this looks fairly imposing, but the good news for us is that we are only considering constant r equal to capital R. So anything there where the derivative with respect to r shows up is going to disappear for us. And so once I plug in just this last term in the equation and substitute that in for my time-independent Schrodinger equation, I end up with a fairly simplified picture where I want to say figure out some solution where a set of constants times the second derivative of the wave function is equal to the energy times the wave function. And folks will try and treat these constants a little bit differently. One thing you might see in the literature is a connection to your physics courses in classical mechanics, where mr squared is defined as the particle's moment of inertia. So sometimes you'll see this substitution for capital letter I. The other thing that you'll see, and what we'll do to make our lives a little bit easier, is to say that let's group together all the constants that show up in this problem and smush them together into a constant variable that we're going to call m sub l for reasons that will become apparent later in the lecture. If you're already asking yourself if this m sub l is somehow going to relate to our quantum number m sub l that we learned about in general chemistry, the answer to that is yes. So we're going to smush together all of our constants. At this point, m sub l is purely just like a mathematical way of cleaning up our solution so that we only have to write one constant instead of many constants. We haven't yet talked about if m sub l has any special meaning to it. So at this point, m sub l, just a variable that I told us to use as your instructor. And we should ask ourselves, what functions would best fit this type of problem? We're looking for something where the second derivative is equal to negative the constant squared times psi. And I would contend that just like in the particle in a box, there's two functions that I know about where the function is equal to its own second derivative. You can use sines and cosines, which you could do for this problem. I'm going to use exponentials in this case because exponentials lead in this particular circumstance to the cleanest looking solutions. But remember, mathematically, sines and cosines and exponentials are equivalent and they're linked together by Euler's formula if you want to know exactly what the correlation is between those two things. So here's what I claim is the answer. Let's go ahead and do a bit of math to show that this is a valid solution to Schrodinger's equation. So what we want to do is we want to take the second derivative of this wave function that I'm proposing with respect to phi. Here's my wave function that I'm proposing. And so my first derivative, well, according to the chain rule, I need to take the derivative of the outside, e to the u's derivative is just e to the u, times the derivative of the inside, and that means that I'm going to pull out a factor of IML. We'll do that one more time, and we'll see once again that we get a second factor of IML, because we're taking our second derivative, times the original function. Now, I squared is equal to -1, and so that means this is equal to negative ml squared times our original function itself. And so that means that the second derivative of this function is equal to negative ml squared times the function. We're good to go. This is a valid solution to Schrodinger's equation. Now, just like we did in the particle in a box, we need to go ahead and take this solution now and turn it from something that mathematically works to a restricted set of solutions that obey what the physics or the underlying concepts of the problem should be. So what's our step from math into a physics or a chemistry world? Well, remember we had some constraints on what the wave function should look like. One of those constraints was that psi needs to be single valued. Now, let's think a little bit about what that means. If psi were not single valued, it would mean that, psi at a given value of phi could be equal to 2 and 5. That would then mean that the probability of seeing the particle at that value of phi was 4 and 25. And I don't know about you, but having one event that has multiple different probabilities doesn't make physical sense. So the reason to have psi be single valued is so that the probability is also unique for a given set of coordinates that the particle could be at. Don't want to have one possible event having multiple different probabilities associated with it. And so this single valued is going to come in because remember, if you remember back to your trig class, when I'm talking about polar coordinates, starting off at an angle of 0 is the same if I loop back all the way around to a value of 2 pi. And pi and plus 2 pi, 3 pi should give the same thing, right? Because we're looping around and around in a circle. So whatever my value of psi of phi is, I better end up with the same answer if I add 2 pi onto my angle. Because again, we're going around in a circle, and so once we make one loop around the circle, 2 pi, we should get back to the exact same point. So let's plug in our solution to Schrodinger's equation and see what that means, if anything, about what m sub l looks like. So here we go ahead and plug in that a times e to the I ml theta, or phi, should be equal to that same function, but now phi plus 2 pi. And so I'm going to employ a couple of different mathematical tricks about how exponentials work. The first is that if I have within the exponent a term plus a term, that's equivalent to the term in the exponent times the exponent times the second term. So I can split up my phi and my value of 2 pi. And then the second rule that we should remember about how exponents work is that if I have something in my exponent that is multiplied within the exponent, that's the same thing as taking that exponent and raising it to a power. So again, my exponent rules. Here's my additivity rule, and here is my rule about powers. And so that leads me, once I apply both of these rules about exponents, to a simplified version of this equation in which I have my original function for phi times a term that's e to the I pi raised to the power of 2 ml. Now, Euler's formula is a famous mathematical theorem that says that e to the I pi is equal to -1. It's sort of a special constant. And so the only way that my equality holds true is if whatever I do -1 to the 2 ml, that has to give me back 1 in order for this to work. And so if ml is not an integer, -1 to the fractional power is not 1. It's complicated mathematically, but it's definitely not 1. If 2 ml is somehow odd, then we're going to get back -1, because if I take -1 an odd number of times, most of those cancel out and I'm left with the term -1 left over. So I need 2 ml to be an even integer in order for this equality to hold true. And so that tells me that m sub l has to be an integer. Now there's nothing in the math that tells me that m sub l has to be positive or negative, and in fact it can be both. And so my quantum numbers that fall out of the particle in a ring problem is that I have some quantized value that I'm calling m sub l, and it can take on values for this problem of 0, plus or minus 1, plus or minus 2, all the way up to infinity. And that is not the same yet as the quantum numbers for hydrogen and the restrictions on m sub l, but it's starting to look a little bit familiar. We at least have integer values of m sub l, and they can be both positive and negative. Just as in our previous problem, note that this quantized value that shows up in our wave function leads us to quantized energy values. So up all the way at the top when we defined m sub l, you'll note that it depended on the energy, so I can rearrange that equation to solve for the energy. And the particle on a ring energy depends on a couple different constants that showed up in the problem, and our quantum number m sub l. And note as a point of clarification that there's 2 times that a lowercase m shows up in this problem. M without the subscript L means the mass of the particle. M with the subscript L refers to our quantum number. And then last but not least, the other thing that we can know about this particle on a ring problem is that, as always, psi has to be normalized. And so it's a little bit useful to show that normalization process just so that we can do a refresher on complex conjugates. So our normalization condition is that the wave function multiplied by the complex conjugate over all relevant space should be equal to 1. In this case, all relevant space means going from 0 to 2 pi, and phi is going to be the variable of integration. My wave function complex conjugate is a times e to the negative I ml phi, and my normal function is a times e to the positive I ml phi. And the great thing about this is that both of these exponential terms cancel out to give me 1. So these cancel out together to give me 1, and I'm left with a squared d phi integrated from 0 to 2 pi. So a constant integral is a squared now times phi, and if I evaluate that between 0 and 2 pi, that's going to give me a squared times 2 pi, and since that whole thing is supposed to be equal to 1, it tells me that my normalization constant is 1 over 2 pi to the 1/2 power. And so with that, now we can officially give, without any unknown constants or variables, our particle on a line wave function. And it doesn't look too bad, but it shows us that in this case, our wave function, it looks very different than our particle in a box wave function at first glance. But notice that this one is kind of like a decaying exponential. So that's kind of interesting. There is a wealth more to say about this particular problem, some of which we'll go through at the end of the semester or in the last third of the semester, but at this point in the course, I've said all that I really want to say about this particle on a ring problem. And so with that, now let's talk about the particle on a sphere. So similar setup to our particle on a ring problem, we're going to consider a particle that now has mass m. It's subject to a potential that is 0 if the radius is equal to capital R, but otherwise it's infinity. And so what that means is that if you imagine like a spherical shell, the particle can go anywhere it wants along that spherical shell, but it can't change its value of R. It's limited to its radius away from the origin being equal to capital R. And we now, because we're in spherical coordinates, have 3 coordinates to deal with. R is the radius, phi, as we've described before, is our polar angle, and our theta variable is our azimuthal angle, if you like to call it. And if you remember, our review of spherical coordinates is that the polar angle goes all the way around the circle from 0 to 2 pi, but our azimuthal angle can go anywhere from 0 just to pi. So it kind of just does half a circle in order to give us an ability to describe anywhere we want on this sphere in terms of spherical coordinates. So analogously to what we had to do with the particle on a ring problem, now we need to take our time-independent Schrodinger equation for the 3D version of the Hamiltonian and convert that to spherical coordinates. So if you remember, we gave a special name to our Hamiltonian when it's the 3-dimensional case. We call this the del squared operator, or the Laplacian, but it's just there to save us some writing. And in spherical coordinates, the Laplacian takes on a particular form. And you're going to have to trust me that this version of the Laplacian is going to make our lives easier, even though the Cartesian coordinate version looks a little bit more simple at the outset. So our Laplacian in spherical coordinates, which is what we need to use, has some familiarity compared to the 2D version. We still need to add up the second partial derivative with respect to r, the 2 in this case over r times the first partial derivative with respect to r, plus 1 over r squared times some funky other operator that we call the Legendrian. The Legendrian is even more complicated. You can see that there's terms that depend on theta, terms that depend on phi, and we have a couple of partial derivatives that are with sine functions smushed in between. And I want to make one mathematical note here that even though you might be tempted to look at these last two sine functions that are on the right side of my screen and say, ooh, maybe those will cancel out. Remember that order of operations doesn't allow us to move around the derivatives. And so we can't simplify this Legendrian any further than I've shown it on this slide. All right, just as before, r in our problem is constant because we've restricted the motion of the particle on a sphere to be on a spherical shell. So we're going to drop all of the terms whose derivatives depend on r. And that leaves us with a time-independent Schrodinger equation that's some constants times the Legendrian operator times psi is equal to E psi. And once again, just for clarity's sake, I'm going to group together my constants that appear in this problem into some variable epsilon. And epsilon, I'm sorry to say, is not going to really have any special value that shows up in terms of its chemical or its physical meaning, so it's purely there as a convenience definition for us. How are we going to solve this? Separation of variables is going to show up one more time. So this is going to be the same process that we used when we were solving the 3D particle in a box, but more mathematically involved. So I've done my best to try and color coordinate it to help us walk through this derivation, and let me give us a breath to look over this and recognize that you will never be required to derive this equation like I'm doing right now. What's important is that you can see this derivation in action and that you can recognize why it is when we get to the end that we have some quantum numbers show up and can see what the wave functions that look like as a solution to this problem. Okay, so our separation of variables technique is going to be to say that the wave function we're looking for, which depends on both my angular coordinates, maybe is some function that I'm going to denote with uppercase theta, which is really just me drawing a big circle and then putting an h on the inside of it. Uppercase theta, a function that depends on my variable theta, lowercase theta, times another function, uppercase phi, my phi function, that depends on my phi variable. And so substituting in this idea of a separated equation back into my original expression for my Schrodinger equation, I am going to see that now I have two functions that I need to operate on with the Legendrian operator. The terms that are additive can be, like, you can operate both of those on it separately using the distributive property, and the terms that are multiplied together, those are the ones that we should not rearrange. So looking at the first term, I note to start off with, so this for this red term, that our variables, this function, I'm supposed to take the derivative with respect to phi, but I'm not doing anything with respect to theta. So since I'm taking partial derivatives with respect to phi, theta, capital theta, my blue function, is treated as a constant in this first term. So I can pull it all the way to the left-hand side of the expression in the second line of my derivation. And then, because I do actually have to take the derivative with respect to phi, this is where phi shows up when I distribute this into my purple bracket term. As for my second term, the opposite is true. Now, I'm taking a bunch of derivatives with respect to theta, but not doing anything with respect to derivatives of phi. So phi can then distribute to the outside of this term, to the outside of my derivatives, to say that it's just a constant with respect to what I'm taking partial derivatives of. And theta is going to have to be left within the partial derivatives, because that is a function where I would actually have to know what capital theta looked like, take its derivative, and then use this operator on it. And once again, you may be tempted to try and rearrange these derivatives, but the correct order of operations, if I knew theta at this point, would be to take the first derivative of theta with respect to the theta variable. Whatever that result is, multiply it by sine theta, and then whatever that combined result is, now take another derivative with respect to theta, and then on the overall result, take that and divide by divide by sine theta. So operators operate from right to left. We have to obey that sequence of events. The operators don't commute, so we can't switch around terms that show up in multiplication. But when we have something that's additive, then those terms can be treated separately. And we can use the distributive property in order to place our terms that are being operated on into the operator in question. Okay, so honestly, that's a little bit of the hard part, is just knowing how to interact these new functions with my operators and with my rules about partial derivatives. From here on out, now I just need to do some algebra. And so, first things first, this was one half of my equation, the Legendre polynomial times theta. I actually need to set that equal to, in this case, negative epsilon psi. So I'm going to go ahead and do that, and that's the term that you get here. And now, if you remember from my discussion of separation of variables technique with the particle in a box problem, our goal is to end up with an equation that has the form some term that depends only on phi plus some term that depends only on theta is equal to a constant. And I've tried to color code this so that really the goal of this derivation game that we're about to play is, can I make all the terms in blue sit together nicely, all the terms in red sit together nicely, and all of my constants show up on the right-hand side of this expression. Or, sorry, to have the right-hand side of the expression equal to a constant. It doesn't necessarily have to be equal to negative epsilon. So how we're going to do that is, first, I'm going to multiply both sides by sine squared theta. And that is because, let me recolor code this. I have a factor of sine squared theta showing up down here that's messing with my first term. So let's go ahead and move it over by multiplying both sides by sine squared theta. So this factor of 1 over sine theta is going to then be equal to, now that will move up to the numerator since I'm multiplying by psi squared, and on the right hand side I also get a factor of sine squared. Next thing I'm going to do is I'm going to divide both sides by my theta function times my phi function. That starts to clean up things a lot better than it was before. And in particular, how it starts to clean things up is that I now have a term on the left-hand side that's just red terms, plus a term on the left side that's just blue terms. That's all good so far, is equal to a term on the right-hand side that, our one bummer at this point is that this term is not equal to a constant, it's equal to something that's a function of theta. So last but not least, I am going to get rid of that by adding epsilon sine theta to both sides. And now, once I've done that, now I have an expression that has a term that depends only on phi, my phi function, plus a term that only depends on theta, and all of that is equal to a constant. Alright, I realized I was using capital letters here. I should have been using lowercase. Alright, so our separation of variables technique is going to hold true once again. And if you remember from our previous discussion, what this meant is that the first term in brackets has to be equal to a constant. The second term, my piece that's a function of theta only, also has to be equal to a constant in order for the right-hand side to be equal to a constant. And because in this case I know that that constant is equal to 0, it means that whatever the constant is for my first term had better be equal and opposite in sign to the constant that my second term is equal to. And I'm going to do something kind of sneaky that you might not have expected. I can call that constant whatever I want, and I'm going to choose to call that constant ml squared. So my red function now says that that piece is equal to a constant, negative ml squared, and my blue piece is also equal to a constant, positive ml squared. And we needed one of those to be negative and one of those to be positive, such that when I add up blue plus red, that gives me back 0, which is what my initial expression told me that that constant had to be equal to, the overall constant. Now, the reason I chose ml squared is because my first equation, once I move that capital phi function over to the right-hand side, if you scroll back up to our particle in a ring example, it's the exact same differential equation that we're solving. So we've already solved it. We don't have to redo all that math, and we can just say, oh, this function is equal to e to the I ml times phi. I've dropped the normalization coefficient briefly, because once we combine together my expression into the full wave function for the particle on a sphere problem, we'll have to renormalize anyway. The second equation, this blue equation, is not something we've solved before. And in fact, the solutions are quite complicated, and deriving them is something that you would do in an upper division math course. The good news is they're known. You can look them up on Wikipedia, and they're called the Legendre polynomials. So what I've shown you is a couple different things to note about these Legendre polynomials. One is that how they relate to my theta function is that I'm going to take the Legendre polynomials as a function of cosine of theta, and there's 2 quantum numbers that show up in this expression. One of those quantum numbers is L, and one of those quantum numbers is m sub L. Furthermore, if we look at the available solutions, not all values of m sub L and L are possible. In fact, L ranges from 0 as the lowest possible integer that fits, or that is a viable Legendre polynomial. And in all of these solutions, especially if I zoom in on them, you might be able to see it a little bit. M is the top number in this indexing scheme, and L is the bottom number. So if I'm thinking about 2, 0, that means that L is equal to 2, m sub L is equal to 0. And m sub L is never bigger than L. Note that even though it wasn't shown at the top of this Wikipedia article, the Legendre polynomials with negative values of m sub L are totally valid. They are the exact same as the Legendre polynomials for positive values of m, and so Wikipedia saved themselves some ink, and they just wrote out the versions of the Legendre polynomials with the positive values of m sub L. So our restrictions on m sub L become that m sub L and L both have to be integers. L can range and be any positive integer, this time including 0. And m sub L is such that for a given value of L, m sub L can range from negative L all the way up to positive L. That really should start to sound familiar, because those are the exact restrictions on L and m sub L that you learned about in general chemistry when we started talking about the hydrogen atom. And that's not a coincidence. Okay, so putting it all together, remember that I claimed that my overall particle on a sphere wave function was equal to a function that depends on phi and a function that depends on theta multiplied together. So I'm going to take my phi function times my theta function, and then, last but not least, I need to normalize this somehow. I am not going to go through the process of normalizing this for you. I'm just going to tell you the answer, which is that it's kind of a complicated square root that depends on m values and on L values and m sub L, and we have our Legendre polynomials showing up times these e to the I m phi terms. So these functions are so special that we're going to give them a name, and we're going to call them the spherical harmonics. And I think it'll be useful for us to, once again, not think about this abstract way of representing the spherical harmonics, but instead look at a table of a couple different examples of this and what they look like. So here are the first couple of spherical harmonics, where our notation tells us that this top index number is m sub L and our bottom index number is L. And so depending on our values of m sub L and L, we get very different functions that show up. And learning how to visualize these functions is a topic that I'm mostly going to leave for our next lecture when we start talking about the hydrogen atom. because again, visualizing a three-dimensional function is not trivial. So we have to make some compromises, I guess, when we try and plot them as chemists. But if I had to show you one picture of what these spherical harmonics looked like, this would be the picture that I would show you. And if those start to really look not identical to s, p, d, and f orbitals, but starting to be hauntingly familiar, it's because spherical harmonics are going to show up in our solutions to the hydrogen atom orbitals. Now, something that may be surprising is that even though these wave functions look so complicated, the energy expression is not. The energy for the particle on a sphere is given by the simple expression energy is equal to L times L plus 1 times h bar squared over 2mr squared. Once again, because this m doesn't have a subscript associated with it, that refers to the mass of the particle, not to the m sub L quantum number. And what's really interesting is that this energy expression just depends on L, not on m sub L. That means that for a given value of L, there are two L plus 1 associated degenerate energy levels. And so, for instance, if L is equal to 0, m sub L has to only be equal to 0 as well. That's my only possible value. So I have one orbital that corresponds to that energy. I really even shouldn't call it a degenerate orbital, because saying that it's, I guess you can say it's singly degenerate. That's fine. So it's a singly degenerate orbital. If L equals 1, now remember m sub L can be anything from negative L to positive L. So m sub L is equal to negative 1, 0, or 1, all valid quantum numbers that fit and solve the Schrodinger equation for L equals 1. That gives me 3 degenerate orbitals. And as my last example on this, if m sub L is equal to, if L is equal to 2, m sub L can take on any value between negative 2 and positive 2, and that gives me a total of 5 orbitals that are characterized by their various quantum numbers that all have the same energy at this L equals 2 value. Sounds kind of familiar. S, p, and d orbitals are going to be showing up in our near future. Okay, so that is all that I want to talk us through today. And I am going to, instead of giving a summary of today, give you my intended takeaways for the lecture. That should be a way of hinting to you that my focus and my reason for giving you this lecture is not so that you can feel like you can solve the Schrodinger equation yourself or rederive this for the particle on a sphere and the particle in a ring. We just told you the answers to the Legendre polynomials rather than having you solve for them yourself. And so our takeaways are going to be a little bit more qualitative for today, and we'll work through in class and on the homework the extent to which we want to deal with some of these situations in a quantitative sense. So my takeaways are that when we talked about rotational motion, it is quantized because the particle is restricted to a particular radius of the ring that it can travel around, or a particular radius of the spherical shell that's available to it. Secondly, rotational motion in 3 dimensions, which is most similar to the type of problem we're going to tackle with the hydrogen atom, since the hydrogen atom is a 3-dimensional object, led to the existence of 2 quantum numbers that both have to deal with the angular degrees of freedom. One of those quantum numbers is m sub L, it's our magnetic quantum number, and the other of those numbers is L, and we call that our orbital angular momentum quantum number. Those have the same chemical meanings as they did in GChem. There are restrictions for this particle in a sphere for allowed values of both m sub L and L, and the particle on a sphere energies only depend on L, such that for a given value of L, there's 2 L plus 1 degenerate energy values. I'm going to add one more takeaway to this list, which is that the wave function for the particle of the sphere is given by a set of special functions called the spherical harmonics. And again, those functions, we don't have a form that's an easy mathematical expression for all of them, but we do have some nice tables that you can look at and that I'll provide for you whenever you need it of what those first couple of spherical harmonics look like. Okay, and that leads us to a cliffhanger for next time, where we're actually, as a class, going to solve the Schrodinger equation for the hydrogen atom. I'm excited about it. I hope you're excited about it. And until then, I look forward to seeing you all in class. Take care, Team Pika.